Hello, my name is Bhavani Simon with Lamar University. This presentation is on computational fluid dynamic simulation for offshore wind turbines. It is based on a thesis presented as part of a graduate program at Lehigh University by Chen-Long Wang. Clean energy is booming and becoming more important than any other energy resource. Wind power is a large and inexhaustible resource that has the ability to make a huge difference in climate change. North America and Europe are installing more and more wind farms because they understand that wind energy is important in developing renewable energy that is reliable and able to reduce our dependence on fossil fuels. The coast of the United States provides a large resource of wind energy, especially for offshore wind technology. Since wind increases with long distances, it will generate more electricity along the coast or even on the shore close to the coast. The National Renewable Energy Laboratory estimates that the US offshore winds have a potential to generate 4 times more than the nation's present electric capacity. The National Renewable Energy Lab also says that in order to make an impact, we would need the US to be using 20% more clean energy by the year 2030. That would mean 54 gigawatts of electricity from offshore wind turbines. In 2016, Block Island Wind Farm became the first offshore wind farm in the United States. It is located 3.8 miles off the coast of Block Island, Rhode Island. European countries spend a great deal of investment for the research of offshore wind turbines. In France, the biggest offshore wind turbine has 73.5 meter long blades. It's located 8 miles from the coast with a capacity of nearly 500 megawatts. The turbines provide the equivalent annual electricity for more than 770,000 people. So, a wind turbine includes a rotor, a nacelle or shell, a tower, and a foundation. Since the effect of the tower on the flow field is negligible, CFD simulations are conducted by considering only the rotor and the blades. The wind turbine used in this paper's simulations has a design similar to the one optimized by the National Renewable Energy Laboratory. Simulations were tested with realistic wind velocity and rotor speed conditions. Airfoils in different cross sections were twisted to improve the quality of aerodynamics of the blade when it is incorporated with the rotor. ANSYS Fluent was used to conduct flow simulations with large eddy simulation, or LES method, which is the mathematical model for turbulence used in computational fluid dynamics. A good geometry and quality of meshing are necessary to perform this simulation. Testing was conducted with the general standards offered by ANSYS meshing. It is critical to have a well-defined meshing for CFD simulations. For torque, the focus is on the blades of the rotor. The entire blade is so large that if we do fine meshing on the whole area, it will take a very long time to compute. Therefore, coarse meshing was done on the edges of the blade and behind the rotor to speed up the calculation time. For the simulations presented here, a velocity of 9 meters per second is considered at the inlet. The rotor speed was set to 1.08 radians per second. The objective was to attain a maximum torque of 2,500 kilonewton meters. Convergence was tested by calculating torque generated using different time steps. The present results are considered against the results reported by previous investigators examining torque generation. The time steps of 0.1 seconds to 0.01 seconds were used as shown in the figure. After the transient response from the system, the torque trended to a steady state with very small fluctuations. Turbulent flow is examined using velocity, pressure, and stress fields. The aerodynamic torque and power produced by the wind turbine was calculated. Outer diameter of the computational fluid domain was selected 3 times larger than the diameter of the rotor to make sure the flow could be seen away from the rotor region. The total length of 350 meters long with a length blade region of about 100 meters long. This simulation included the whole rotor region while previous investigators only considered 1/3 of the rotor region in their simulations. Therefore, the simulations presented here are a better representation of actual wind turbine operations. Large eddy simulation method is a proven to be reliable tool to study complex turbulent flows. For the wind speed of 9 meters per second, the torque generated by the wind turbine is predicted to be 1,806 kilonewton meters. If you remember, the goal was 2,500 kilonewton meters. The power generated by the wind turbine was calculated to be 1.95 megawatts, which means that this design met 72.2% of the maximum potential power. The author of this paper felt that it was clearly demonstrated that the torque generated and the flow field presented were the result of fully converged simulations. Thank you for your time.